Good morning, everyone. Afternoon, evening, good night. Whenever it is you happen to be watching these, I'm sorry, that's the wrong side. Whenever it is you happen to be watching these, I hope everybody's having an amazing day, as per usual. No intro music today because someone thought it would be cute to flag one of my videos for copyright infringement because I played a song. Yay! So no more of that. Okay, so let's talk about today about a dirty little D word of calculus, differentiable. Differentiable means that it has a derivative. If something is differentiable, it means that you can find the derivative of that thing. So when you're looking at this, the proper definition of differentiable is the property possessed by a function at x equals c if f of c exists. Being differentiable requires a couple of different things. And there's going to be two key words to this. I want you to write these down. Smooth and continuous. Now the continuous piece is pretty self-evident, right? I mean, we've been dealing with continuity for quite a while. For example, in number 1 here, it says, if a function is not continuous at x equals c, then it's also not differentiable at x equals c. And that one's pretty obvious because the limit is not the same at c. The limit doesn't exist there, right? So the limit doesn't exist here because the limit from the left, limit from the right is different. So if it's not continuous, then it's also not differentiable. All right, that pretty much makes sense. Down on number 2, if a function has a sharp turn, we call that a cusp. You don't really need to necessarily remember that word, but I'm going to be using it a little bit here. We call it a cusp, or you could just say sharp turn if you forget the word cusp. The function is not differentiable because the right and left-hand derivative are not the same. Remember that the derivative is the limit of the slope function, right? It's the limit of the rate of change. Well, if the rate of change on the left is different than the rate of change on the right, then the limits are not going to be the same. See, the derivative over here, the limit is -1. The derivative on the left and the derivative on the right is 1. Therefore, there is no derivative at 5. There's no derivative in any sharp points. Okay, so it's got to be smooth and it's got to be continuous. And the last one here on the bottom, it says if a function has a vertical tangent, it is not differentiable. Think about what it would take for a vertical tangent to be a vertical line. That means that your slope would have to be undefined, right? An undefined slope is a vertical line, kind of like at 0 right here. This has a vertical tangent. It goes right here. Right? Because of this vertical line here, because of that vertical tangent line, there is no derivative at x equals 0. No derivative there. Now you could find the derivative at other places, just not there. Same way with this one, with both of these up here. You could find the derivative at other places, but overall we would not say it's differentiable because of that one place. So it's kind of like, I could say up at the top, I can say that this is continuous from here to here, right? So if I limited my interval, I could say it's continuous. Same thing with derivatives. If I limit my interval, I could say that it is differentiable. But if I'm just looking at it as a whole, this is not continuous, therefore it's not differentiable. This is not smooth because of this point. Even if I eliminated that point and said it's only from here to here, yeah, I could say it has a derivative from there to there. But overall, as a whole, remember that's what I'm looking at here, as a whole, it is not differentiable because it's not a smooth and continuous curve. Same thing down here. The only point that is not differentiable is 0, but because of that, it kind of makes the whole thing, as a whole, again, not differentiable. Okay? So let's go over to the back here and let's actually figure out what some of these are going to look like, what some of these questions may look like. For example, example 1 here says state where it's discontinuous and state where it is not differentiable in y. Well, let's throw some values in here. This is -1. This is 2, 3, 4, 5. This is 6, 7, 8, 9, 10, 11, 12. That's probably okay. And here at 11. Okay, so I'm looking at where is it not continuous? Where is it discontinuous? Well, there's only one spot where it's discontinuous, and that's where you have a jump in your graph. Remember, I never assume that this thing stops. I assume it keeps going. So for number 1, where is it discontinuous? It is discontinuous at x equals 2, right? And that's the only spot where it's discontinuous because you have a jump in your graph. Everywhere else is continuous, even though you do have a cusp here and here. So that is going to affect where it's differentiable. Where is it not differentiable and why? So I'm going to say that it is not differentiable. And I've got a few places this is happening at, so let's just list them off real quick, and then we'll look at why. First, at -1. So it's not differentiable at -1, and what's the reason for that? Well, that's a cusp, right? Not differentiable at x equals 2. That's because it is discontinuous here. It is not differentiable at x equals 6 because it's a cusp. It's a sharp turn, right? And it's also not differentiable at x equals 11 because at x equals 11 right here, it seems like we are going to have ourselves a vertical tangent. Vertical tangent. Okay, so let's actually get into this a little bit here, and let's prove some of these algebraically by showing our work. So example number 2, we have a piecewise function, x squared plus 1 to the left of 2 and including 2, and 4x minus 3 to the right of 2. Well, the first thing we need to do is figure out if this thing is actually continuous at 2. Okay, because if it's not continuous at 2, then it doesn't matter if what the derivatives are going to be. So to see if it's continuous at 2, plug a 2 in for both of these. So you got 2 squared plus 1. You got 4 times 2 minus 3. So that's 5, and 8 minus 3 is 5. Okay, so because you get 5, because these are both the same here, I'm going to say it is continuous at x equals 5. What I've done here is check to make sure that there is not a jump in the graph, like up here. If I would have gotten 2 different values, I could have stopped there and said that no, it's not differentiable. Okay, since it is continuous though, that's first, tell me if it's discontinuous. Second says to tell me if it's differentiable. So I got to check the derivative from the left and the right, kind of like you check the limit. You got to check the derivative from the left and the right. So first, we'll do f prime from the left. That's going to be f prime of 2 is equal to the limit as x goes to 2. Zoom in here a little bit, you can see this work a little bit better. The limit as x goes to 2 of x squared plus 1, because I'm on the left, minus 5, what we got if we plugged in our value of c here. Remember, c is where we might have an issue, over x minus c. So these two combine to give you minus 4. So let's set this up here. This is going to be the limit as x goes to 2 of, let's split that thing up here. x plus 2, x minus 2 over x minus 2. Get rid of that. And we've got the limit of, as x goes to 2 of x plus 2. That's going to be 2 plus 2, which is 4. So the limit from the left is 4. Or the derivative from the left is 4. Let's find the derivative from the right. F prime of x from the right. Scooch over here. From the right, I use this bottom one where x is greater than 2, because greater than 2 is to the right of it. F prime of 2 is the limit as x approaches 2. Oh, and technically, I could have put negative here and negative here since we're going from the left. I'm going to go ahead and put a positive here since we are coming from the right specifically. And that's 4x minus 3 minus 5 over x minus 2. Okay, 4x minus 3 minus 5, this is going to give me a negative 8. So this is going to be the limit as x goes to 2 from the right. Now this is 4x minus 8, so let's say we take a 4 out of there and we get x minus 2. Because I know that's what I'm looking for anyways. So the limit is 4. Okay, so do you see how the left-hand limit and the right-hand limit are the same here? Because of that, I'm going to write the left and right derivatives are the same. Therefore, f of x is differentiable. Ran out of room. Differentiable at x equals 2. Because let's face it, if there's going to be an issue with this thing, it's going to happen where the piecewise function splits. It's going to happen at 2. Same thing for number 3. Where the piecewise function splits is where we might have a problem with differentiability, so that's the only place I need to check. You know, unless there's a square root, unless there's like a divided by 0 or something else going on in here. But there's not, so let's move on. Down on the bottom here, example 3. First thing I'm going to do is plug into both of these and see what it looks like coming from the left and from the right. From the left here, down here, x is less than 2. From the left, 2 times 2 is 4. From the right, you've got 2 squared, which is 4. Alright, so we're going to say therefore it's continuous at x equals 2. Excuse me. Sorry about that. So we know it's continuous now. Let's see if we can find derivatives for it. So we've got f prime of x from the left. Let me zoom in just for this portion here so you can see this a little bit better. F prime of x from the left, we've got the f prime of 2. Excuse me, I'm sorry. And from the left, we use this bottom one here. So from the left, we're going to use the one where x is less than 2. All right. So from the left, we've got the limit as x goes to 2 from the left. And to the left of this, we use f of x minus f of c over x minus c. Right? 2x minus 4 over x minus 2. We can factor out a 2 out of there pretty easy. Limit as x goes to 2 from the left. And that's going to give us 2x minus 2 over x minus 2